Okay, time for the main event of today, voltage division. I guess there are two main events, voltage division and current division, but once you understand voltage division, current division is going to be pretty easy. So the idea behind voltage division is that there's one other thing we can do with two resistors that are in series. Remember that last time we saw that we can combine them together into an equivalent resistance. But there's one other thing we can do if we don't want to combine them together. If what we really want to do is find the voltage across each of those two resistors, and if we also happen to know the total voltage that appears across both of those resistors, then we have a special set of equations that can be used to calculate the voltage across each of them. So essentially the question that we're asking ourselves is, how do R1 and R2 share V sub S? We understand that if we take the bottom terminal here to be 0 volts, then the top terminal is at V sub S. So this is V sub S here, and we know that down here is 0 volts. So V sub S appears across the series combination of these two resistors, but the question is, how much appears across each of them? And like all good engineering questions, the answer is, it depends. The question is, what does it depend upon? In this case, it depends upon the values of V sub S, R sub 1, and R sub 2. And here are the equations that we can use to calculate V1 and V2. It is simply V sub S, the total amount of voltage, multiplied by a fraction. So that makes sense. We're going to get a fraction of V sub S to be V1. The question is, what is in this fraction? And the answer is, it's R1 over R1 plus R2. Well, R1 plus R2 is the total amount of resistance in the series combination. And R1, well, that's the resistance whose voltage we want to know. So another way of seeing what this fraction is this fraction represents what percentage of the total combination of these two resistors is contained within R1. That's the same percentage of the total voltage that will be assigned to that same voltage. And so if you say, oh, R1, that's 75% of the total resistance, then it's going to get 75% of the total voltage. If R1 is 10% of the total resistance, then it'll get 10% of the total voltage. It's actually extremely intuitive. The analogy that I love here is you imagine if you have two dogs, you have a big primary dog and a second, much smaller backup dog. And if they're eating out of the same food bowl, well, the big dog is clearly going to get more of the food, unless the little dog is a bully, and we'll assume that isn't the case here. So the big dog will get more of the food in the same way that the big resistor will get more of the voltage. And you can see here that the equation for V2 is exactly the same. V2 equals Vs, the total voltage, multiplied by a fraction, and that fraction represents what percentage of the total resistance is contained in R2. Now, an interesting thing is that absolutely, positively, V1 plus V2 has to add up to Vs. We absolutely know that. By Kirchhoff's voltage law, that has to be the case. Minus Vs plus V1 plus V2 equals 0, so Vs equals V1 plus V2. So when you do a calculation like this with real numbers, you can double check whether or not your answer is reasonable. Another thing you can double check is, does the larger resistor get more of the voltage? And is it roughly in proportion to how much more resistance it has? If so, then it seems like your answers are probably pretty reasonable. So let's look at a numerical example here. I've actually shown you an example here in part A where we have 3 resistors. And I really only want to know the voltage across the 5 ohm resistor. So what I'm going to do is I'm going to combine the other 2 resistors together. So the 10 ohm and the 15 ohm, I'm going to combine those together into 25 ohms. And now I'm down to the circumstance where voltage division can apply. I have 2 resistors. They're in series with one another. I know the total voltage that appears across the combination, and I want to know the voltage that appears across one of them. So you can see here that Vs is 15 volts, R1 is 5 ohms, R1 again is 5 ohms, R2 is 25 ohms. Remember that 25 is the combination of 10 plus 15 from over here. When we do this arithmetic, we get 2.5 volts. Is that possible? Is that reasonable? Well, it has to be less than 15, and it is. And I'm looking here at 5 ohms versus 25 ohms. Well, the 5 ohms, that's definitely the smaller dog. So it's definitely going to get less than half of the 15 volts and probably quite a bit less than half. And half of 15 would be 7.5. So yeah, 2.5 seems like it's a reasonable answer. Now, once we know that it gets 2.5 of the volts, well, that means that 12.5 goes across the 25 ohms, or we could say 12.5 goes across the combination of the 10 and the 15. So that's a perfect example of a place where we could apply voltage division a second time to find what the voltage across the 10 ohm and the voltage across the 15 ohms are. We weren't asked to do that in this case, but we certainly could if we wanted to. So now you have enough information to solve the voltage division example problem. Then come back and we'll talk about current division.